So what I want to talk about today is a big theorem in functional analysis and mathematical physics called Stone's theorem. And there's a few variants of it. I was talking with Tim about this earlier. It's like the Fourier transform. Everyone puts their I or minus I wherever you want, which screws up the notion of skew adjointness. So I'm just going to pick a way to have my operators with an I and stick with it throughout the day. So let me start with just a motivation from basic ODEs. Hopefully we remember this stuff. Consider the basic ODE in one dimension. U prime of t plus I a u of t equals 0 with some initial condition u of 0 equals u0. Basic ODEs. How do we solve this? By sight. What is the solution? A is a number, I is the square root of -1. You solve this by sight, right? U of t equals u0 e to the minus I a t. Basic ODEs. So what I'm going to study today is how to solve this simple problem in a much more general setting, in a Banach space. So instead of having a number a here, I'm going to have an unbounded self-adjoint operator over a Hilbert space. The solution will be the same, e to the minus I a t, but we would have to understand what in the world does it mean an exponential to an unbounded self-adjoint operator. Doesn't make sense. Well, you can make sense of it, but in any case, that's where we're going to solve this type of problem. So let me actually keep this over on the other board so we can remember it for when we get there. So we have u prime of t plus I a u of t equals 0, u of 0 equals u0, implies u of t equals e minus I a t u0. All right. So let's just jump right in. I'm going to start by telling you who cares about Stone's theorem, and people in functional analysis and quantum mechanics. So this comes up and is very important in the setting of quantum mechanics, because if you have a Hamiltonian H, let's say H sub v with some potential v, then the time evolution of your quantum mechanical system is governed by the operator e to the minus I h v t acting on your initial data psi 0. So again, we're going to have an exponential to an unbounded operator, so we have to make sense of this. So what Stone's theorem is telling us is that these things are related to this type of problem. So these things are related to well-posedness of these Cauchy problems, in the sense that as long as you're in the setting of quantum mechanics, as long as your Hamiltonian is self-adjoint, you have well-posedness of the corresponding Cauchy problem. So this is the basic idea of Stone's theorem. So to do that, we're going to need a bunch of functional analysis. So let's jump right in and let me tell you what a C0 semigroup is. So here X will be a Banach space always. Many times I will just assume it to be a Hilbert space to make things easier. So X is going to be a Banach space, a family of operators I'm going to write it in this way. T of t for t positive. Little t I'm always going to be thinking of as a time index because I'm thinking about some time evolution of some field. Yeah, whether it's some quantum mechanical field, an electromagnetic field. In any case, think of t as time. So a family of operators of, let's call them bounded linear operators on X is called a C0 semigroup. Or a strongly continuous semigroup. If the following three conditions hold. 1. T of 0 is just the identity. 2, this is called the semigroup identity, which says T of t plus s should be equal to T of t, T of s for each positive t and s. So far, these first two, you can kind of see a group structure, which is why it's called a semigroup. And then finally, you have a strong continuity property, which says, let me see which variable I used. For each u in the Banach space X, you have that the following limit holds. Limit as h goes to 0, norm of t of t plus h, u minus t of t u, norm on x, this is equal to 0. This is the so-called strong continuity property. So this is the definition of a strongly continuous semigroup. I'll give you some examples in a second. But first, I want to talk about its generator, which is going to be the star of today's talk. So given a strongly continuous semigroup, T of t, its infinitesimal generator is the unbounded operator let's call it A, defined by, is going to basically be defined by differentiation. A acting on x, by definition, is going to be the limit as h goes to 0, t of hx minus x all over h, with domain d of a is the collection of x in your Banach space X, such that this limit exists. Are we all familiar with unbounded operators on the Hilbert space? Yes, so in general, this operator is not going to be defined over the whole Banach space. It's only going to be defined on a subset, the domain. So this operator is only defined for vectors in the domain here. So its infinitesimal generator is generally an unbounded operator. This terminology is a bit strange because an unbounded operator can in principle be bounded. But in general, the infinitesimal generator of the C0 semigroup is defined in this way with the domain where this limit exists. So let me give you a couple examples, one from PDEs and one a little bit easier to deal with. So there are many, many different kinds of semigroups. First example, heat equation in Rn. dt minus Laplacian u is equal to 0. Let's say we have 0 boundary data with initial data, some function. Then it turns out the operator A, defined to be the Laplacian, is the infinitesimal generator of a C0 semigroup. I didn't tell you what my Banach space is yet. Over X is going to be the Sobolev space W2P, intersect W1P 0 of omega, and this 0 is expected because I have 0 boundary data here. So this is one example of the infinitesimal generator versus semigroup. This semigroup is actually called the heat semigroup, as it's the solution of the heat equation.
What are the operators?
This is Laplacian.
What are the operators generated?
Oh, okay. So you know what the representation of the heat equation is given by this integral against this heat kernel. This is basically the group of operators indexed in time. But in general, it could be very difficult to know what exactly the group is, semigroup is. Something more easy to work with. Let me consider a simpler Banach space, and we'll actually do 2 of the calculations. Let's take x to be the continuous functions of compact support on R, and I'm going to let t of t denote the shift operator. So how is it going to act? It's going to act on functions f at a point x is given by f of t plus x. Then the claim is that t of t is a C0 semigroup. So just a few things to check. Remember, we have to check that at 0 is the identity. T at 0 is the identity. I think we can agree on this. Nothing too difficult here. Now we have to check the semigroup property. So I have to look at t of t, t of s, acting on the function f, evaluated at x, is going to be t of t, f at x plus s, which is f at x plus s plus t, which after rearranging is exactly t of s plus t, f at x. So the semigroup property is satisfied, and strong continuity, this is just an exercise. You can check it. So this is indeed another C0 semigroup. So they come up very often. So let me tell you the main theorem for C0 semigroups and the relation to Cauchy problems of this form. Yeah. Something of this, well, I'll show you in a second what I mean, but something like this when A is going to be, in this case, A is going to be the infinitesimal generator of a strongly continuous semigroup. Okay. So we're going to see, eventually with Stone, is that once you're the infinitesimal generator of a semigroup, you have well-posedness. All right, so this is the main theorem, let's call it the semigroup theorem. I'm not going to prove it. So I'm going to let t of t, a C0 semigroup, with infinitesimal generator A. Then there are a couple things. First, there exist 2 numbers, omega bigger than or equal to 0, and m bigger than or equal to 1, such that the operator norm on x is controlled by m e to the omega t for each t positive. Notice in particular that omega is a positive number here. The more interesting case is under what conditions will you have decay? So if this is the solution of some Cauchy problem, when will the solutions decay? When this number is negative. And how can you relate this number to the spectrum of A? But I'm not going to go into that. This is going to always be true. You can find some omega positive and some m bigger than 1, such that this is true for each positive time. And finally, here's the key. For x belonging to the domain of A, remember we have an unbounded operator, so in general I cannot take general initial data. I have to restrict myself to the domain of A. So for x in here, in particular, when I apply the semigroup, I stay in there. And here's the big one. If I look at d by dt, t of t x, this is equal to A t of t x. Now, what do I mean by d by dt here? So now we're talking about general differentiability. So for example, if I differentiate from the right, d by dt plus of t of tx will just be the limit as h goes to 0 of the following quantity, t of tx minus t of h plus tx all over h. And the derivative from the other side is defined similarly with a minus sign here. So what in particular does number 2 mean? So for number 2, if we set u of t to be the semigroup acting on my initial data, then u of t satisfies u prime of t is equal to a u of t, which is more or less this without an I. And yeah.
Sorry, the norm here, where you bounded by n to the omega t, what is that subscript?
This is an operator, so this is an operator norm.
Oh, was that it? Okay.
This is an L, sorry.
Yeah.
Sorry, yeah.
Thank you.
So if we set u of t to be the semigroup acting on the initial data, then u of t by the second part here satisfies u prime of t equals au, and u of 0 will actually be x. So somehow when I have the infinitesimal generator, I can solve the following Cauchy problem. All right, so this is the idea, but now we're going to have to figure out how do we get an infinitesimal generator and how do we get to a semigroup. So time to review some more functional analysis. So let me recall, an operator A is called closed if its graph is closed. In x cross x. This is what I mean when I say closed operator. Then another big theorem says the following. If you have an unbounded operator, so since everything in general here is unbounded, I have to be extremely careful with the notion of adjoint, with the notion of density and closedness. So I'm going to be a little bit pedantic in stating the theorems, but this is just because the operator A is unbounded. If it's bounded, you kind of don't have these problems, but in general it will be only unbounded. So if A is the infinitesimal generator of a C0 semigroup, somehow, if we can show that this happens, then A is densely defined, i.e. the closure of the domain is equal to x, and A is actually a closed operator. So we're going to need this later. All right. So this is what closed means. Now I need some more functional analysis. Let's remember Hahn-Banach theorem. Not going to state it, but I will use it. So let now x be Banach, x star its dual. Have we all seen the Hahn-Banach theorem before? All right. So x in a Banach space, x star will be its dual. For each x in the Banach space, I'm going to define the duality set capital F of x is going to be set in the dual by the following. F of x will be defined to be the set of x star in the dual such that x star of x is equal to the norm of x squared is the norm of x star squared. In particular, this is not empty. I remember doing this exercise in functional analysis. This is not empty by Hahn-Banach theorem, one of the versions. So I need this duality set. And let me just make a quick remark. If it were in the Hilbert space setting, then the duality set is just the point x. so it reduces nicely. But in general, for a Banach space, I'm going to define it this way, and is not, of course, I mean empty here, not empty by the Hahn-Banach theorem. All right, so that's about all the functional analysis I need to review. Now I can get back to the semigroups. So I need another property of semigroups. Give you a definition. So an unbounded operator defined on a domain into X is called dissipative if for each X in the Banach space, there exists an element in the duality set f of X such that if I look at the real part of the following quantity, X star on AX, the real part of this is less than or equal to 0. So let me put this over here because we're going to need it later. Yeah. When I have parentheses, it's going to be an inner product. For most of the time, you can just think of X as a Hilbert space. All right, so before stating the giant hammer that I need, let me tell you one more property of semigroups, a different kind. It's kind of intuitive.
So if you take this in another space setting and you got that, then what's the point of
I mean, in the Hilbert space, yeah, there's no point. But I'm stating,
theorem? What does the theorem even mean?
there's no theorem. This is a definition.
Or, sorry, I guess what does the definition mean?
In the Hilbert setting? Or the Banach? Which one?
In the box, you would assume that X star, that's like a duality theorem?
Yeah. So this is an element of the dual space X star.
So that's not it.
Yeah, so it's not an inner product outside of the Hilbert space, it's an application.
Yeah. So let me I'll write everything in the Banach space, but you can think of a Hilbert space to make it easier. All right, so a family of operators is called a contraction semigroup if, as you can imagine, the norm is less than or equal to 1 for each positive time. Pretty.
Hilbert setting, all it was saying is that the eigenvalues that all lie on the left hand.
Yeah, exactly. All right. Well, okay, so I'm going to try and get to stone, which I hope I will, but I'm going to need to plow through some big results that I'm not going to prove. Maybe if I go again later this semester, I can prove the following theorem.
Sorry,
Yeah.
question. We're doing things over R, over real
No,
space? Okay.
complex.
Complex, okay.
Yeah. Haven't gotten there yet, but we're going to need complex.
That's fine.
Yeah, because then we're going to deal with an I here, so the I is going to matter.
Oh, yeah, of course, okay.
Yeah. So let me state the major hammer. This is called the Loomer Phillips theorem. Maybe I can prove this another time. It says the following. You have a densely defined operator on a Hilbert, Banach space, whatever you want. That is also dissipative. We're going to see why I introduced this weird notion of dissipative in a second. So suppose the domain of my operator is dense and I have a dissipative operator. Suppose also I can find a number. Let me call it lambda 0, a positive number, such that the range of lambda 0 identity minus A is actually equal to x. Suppose I have all these conditions, then what can I conclude? I can conclude that A is the infinitesimal generator of a C0 semigroup of contractions. Which from the first theorem tells me I have well-posedness of the underlying Cauchy problem. So I need three things: densely defined, dissipative, and I can find a number lambda 0 such that this range is actually equal to x. Then I'm the infinitesimal generator of a contraction semigroup. So I'm not going to prove this because this is a very big result, but I'm going to prove the main corollary that we need. Yeah, I put it there. Okay. So I still haven't told you what Stone's theorem is. I hopefully can get there in maybe 10 minutes. But the main corollary of this theorem that I need is the following. So again, A will be densely defined and closed. So if A and its adjoint, I haven't told you what the adjoint of an unbounded operator is, but you can make sense of it. So if A and its adjoint are both dissipative, then the conclusion holds. A is the infinitesimal generator of a contraction semigroup. So this I will prove. So it's a corollary of this. So by the theorem, enough to show the following. The range of identity minus A is equal to x. You agree? I take my lambda 0 as 1. If I can show this, then by LP I'm done. So the goal is to show this. So I'm going to skip over some of the stupid little details about being densely defined and all that. But basically the idea is this. If the range of the identity minus A is not equal to x, then I'm going to employ again Hahn-Banach. I can find an element of the dual that is not 0 such that x star acting on x minus ax is equal to 0 for each x in the domain of A. It's a simple exercise application of Hahn-Banach theorem. Passing to the dual, this actually will tell us that x star minus A star x star is equal to 0. Why do I care about this? Well, another machine that I'm going to have to use and not prove is the following. It says if, let's say A is a dissipative operator, so you have this condition over here. This is actually equivalent to the following. It's equivalent to saying that the norm of lambda identity minus A acting on x is bigger than or equal to lambda norm of x for each x in the domain of A and for each lambda positive. This is another machine that I need in order to even get to Stone's theorem. But I'm going to use this theorem here with this. Why? Because A star, by assumption, is also dissipative. So lambda equals 1 here implies x star minus A star x star is bigger than or equal to norm of x star. But from this guy, from Han-Banach, we know that this is equal to 0. This implies that x star is equal to 0. This is a direct contradiction to definition of x star. So this tells us that the range of the identity minus A is equal to x, and by LP we're done. Okay? Simple contradiction argument, yeah.
Quick question about the definition of dissipative.
Mm-hmm.
For over Hilbert space, is the condition for that corollary on A star, is that going to be redundant, or am I?
The condition that A star is also dissipative?
Yeah.
You don't know that A star is, so it would be redundant if A was self-adjoint, but we don't know anything about the relationship between A and A star. Oh, yes, I see what you're saying. You're going to see this in a few minutes. You're going to, yes, I see what you're saying, yes. In a few minutes, it's going to come up.
Okay.
Yeah. All right, so this is the main core.
Isn't that just from the definition of the essay?
Yeah, basically, yeah. If this is going to be equal to, in the end, we're going to see this is equal to 0, pass to the adjoint, it's going to say, yeah.
Okay, yeah.
No, I don't remember. Okay, so this is the main corollary that we need for the proof of Stone's theorem. Now I can finally get to Stone's theorem. So this is a remarkable result, proved by Stone in the Annals in 1930, and then again by von Neumann a few years later. Before I write it down, let me just tell you in words what the idea of Stone's theorem is. There are a couple parts, and what I consider Stone's theorem is only one part of the main theorem. So this is a remarkable result that basically says, if you have a Hilbert space, or Banach space, whatever you want, let's say Hilbert space, you have an unbounded operator A, which you somehow can show is self-adjoint. That's all you need in order to get well-posedness of the Cauchy problem. Self-adjointness will give you immediately well-posedness of the Cauchy problem via the semigroup theory. Because Stone will tell us that if A is self-adjoint, then depending on your choice of I, minus IA will be the infinitesimal generator of a C0 semigroup. Use the semigroup theorem at the beginning, and you get well-posedness of the Cauchy problem. So Stone is telling us all you need is that the underlying operator A is self-adjoint. So let me give you the setup and how I'm going to use the I's. So now I'm going to a Hilbert space to avoid all this mess. A is going to be an unbounded operator, as usual. And in order to make sense of the adjoint, I need it to be densely defined. Fine. So given A, I'm going to define the operator IA. I here is always going to be the square root of minus 1. IA, so here comes the complex analysis, why we're not working over the reals. IA is going to be defined by, I have to specify a domain. The domain of IA is just going to be the domain of A. And IA acting on a vector x is going to be IAX for x in the domain of A. So it's exactly what you would expect it to be. You just have to be a little bit careful because it's unbounded, so you have to specify its domain, but the domain is going to be the same. So, and this is the domain of IA. Well, it's the same. Now I can state the theorem that we're going to prove. So here it is. First part, which I guess some people consider this part of Stone's theorem, I consider only the second part of Stone's theorem. So under this setup, the first part says A is self-adjoint. This is equivalent to saying that IA is skew-adjoint in the following sense. IA star is equal to minus IA. That's the first part. Finally, the main theorem that I want to prove, stone. What does it say? The operator minus IA is the infinitesimal generator of a C0 semigroup. If and only if A is self-adjoint, which is what I was saying. As long as you have self-adjointness, huh?
Sorry, guys. I'm impressed.
Yeah, I know. I mean, so as long as you have self-adjointness, you have well-posedness of the Cauchy problem. It's amazing. All you have to do is prove that it's self-adjoint. Okay, fine, it's an unbounded operator, so you have to be careful with the domains of definition, but still, Stone says you only need self-adjointness of the underlying operator. So let's prove it. I don't want to get rid of that, so let me put the main corollary over here, because we're going to need it. So densely defined blah blah, A star, dissipative, implies A is the infinitesimal generator of C0 semigroup. I'm going to drop the contraction thing because I don't need it anymore. But all right, let me put this here. We're going to need it in a second. Let's start by proving the first one. So let's show that A is self-adjoint if and only if IA is skew-adjoint. So let's suppose that A is self-adjoint first. Now before I continue, let me mention, so where the confusion comes in sometimes is people put I's here or minus I here or whatever, so I'm going to keep an A here and an IA there. So if you go and look in a book, you might have an I in a different place or a minus I somewhere. Suppose A is self-adjoint, that X belong to the domain of A star, Y belonging to the domain of A. We want to show this equality. So if I look at minus IA star X on Y, I'm going to keep a minus sign there for a reason. So I'm going to push the I to the other side. This is complex. So this is going to be A star X IY plus IY. Let me push the adjoint to the other side. This is going to be X A on IY. This is Y. Huh? You see it? Okay, so this is going to be X IAY. I can push the I outside. Now let me bring IA together to the other side. This is going to be IA quantity star X on Y. And this is going to give us exactly what we need. This tells us that IA quantity star is equal to minus I A star, but A is self-adjoint, minus IA. Done. So that's the first direction. Let's go the other way. The other way is easy, actually. Conversely, let us suppose that you have the skew adjointness, IA star is equal to minus IA. I'm going to be a little bit sloppy and not worry about the domains, but this is going to work out nicely. So I'm going to show that A star is equal to A. So A star, let me introduce, let me say minus I A. So this is I squared minus 1. This gives me minus 1 plus 1. So this is everything star, introducing two i's. So the star hitting the first I turns this into I times the rest of it star. But IA star is minus IA. This is I minus IA. I squared is minus 1. Minus 1 gives me A. A star is equal to A, and so A is self-adjoint. Good. So the first part is done. So we actually need the first part to prove Stone's theorem. That's why I needed to do this. Okay? All right, I want to keep the setup in the theorem, so can I erase this part? And let's get to the proof of Stone. Again, I'm going to suppose that we've done a couple exercises just so we can get through the proof. Let me start with the direction, the forward direction. Suppose minus IA is the infinitesimal generator of a C0 semigroup. Now let me put a name to it. Let me call it T of T. Functional analysis exercises. T of T is an operator, right? On a Hilbert space. It has an adjoint. Let's call it T star. So T star of T, the first one is the dual semigroup, whatever this may mean, of T of T. And for each T positive, T star of T is actually equal to T of minus T. There's the first exercise. Pretty straightforward. And then the second one is that T of minus T will be the semigroup generated by minus my underlying operator. Minus, the underlying operator is minus IA, so this is IA. Two pretty straightforward exercises. So I'm going to assume that we have these two things, and we're going to use this to prove Stone. So we suppose that minus IA is the infinitesimal generator of a C0 semigroup T of T. Then for each element, let me call it U0 in the domain of my underlying operator, we have the following. IA U0. Remember, by definition of the infinitesimal generator, this was defined in terms of the limit via differentiation. So this was the limit. I don't remember if I used H or T, and let me just call it T. So IA is the infinitesimal generator by 2 of T of minus T. So this is T of minus T U0 minus U0 over T. But by part 1 of the exercise, T of minus T is T star of T, U0 minus U0 over T. And this will be minus IA star acting on U0. So here we're relying explicitly on these two exercises. So what does this say? This says that minus IA quantity star is equal to IA. And after changing the minus sign by part 1, A is self-adjoint. This is why I need part 1. All right, so we proved the forward direction. Let's prove the interesting direction. Self-adjoint is all you need. So now we're going to suppose A is self-adjoint. then if I look at minus IA quantity star, using the fact that A is equal to A star, this will be minus IA, which is IA. Well, if you want, pushing the star across the I first gives me I times minus IA, which gives me, wait a minute. This gives me plus, hold on. Minus IA star is going to give me minus IA. This is actually star, but A is self-adjoint. Minus minus gives me plus, so this should be plus IA. Sorry. All right. Now for each x in the domain, of minus IA, I'm going to look at exactly this. I'm going to show that this quantity is equal to 0. Then I'm going to pass the adjoint, show that that quantity is also equal to 0, which means that A and A star are dissipative, or minus IA and minus IA star are dissipative. Main corollary gives me the result. So what I need to show is this for both minus IA and its adjoint. So that's where we're going. So I'm going to look at minus IAX and see what happens with this guy. This is going to be equal to, so minus IA, let's push this guy to the other side. This is going to be x minus IA star x. But minus IA star is IA. This is x IAX. I'm going to introduce two minus signs now. You'll see why in a second. This is equal to minus x minus IAX. And then I'm going to introduce the complex conjugate. Write this as minus IAX x conjugate. I have the same thing here is equal to minus its conjugate. This implies that the real part is equal to 0. This tells me that minus IA is dissipative. But since this is equal to 0, like we were saying before, push it to the adjoint now. This tells us that minus IA star is also dissipative. So if an operator and its adjoint are both dissipative, by the main corollary we have that minus IA is the infinitesimal generator of a C0 semigroup. And that is Stone's theorem. So really what you only need is self-adjointness of the underlying operator. Yeah.
Question, when you said something about, so to get the adjoint semigroup, you take T of minus T?
Yeah.
When we originally defined a semigroup, I think we said that it was only for positive T.
Yeah, there's a notion of dual semigroup.
Okay. And that...
And I just ignored all of that.
Fair enough. Okay.
So given a semigroup, you have the notion of a dual semigroup.
Okay.
So it makes sense to talk about the dual. So you have to go through the theory of dual semigroups to make sense of these exercises. But it's possible, trust me.
Sounds good.
Yeah. So I just ignored that.
Yeah.
But you're right, it's a lot more subtle than I let on. So Stone tells us A is self-adjoint. So minus IA is the infinitesimal generator of a semigroup. What does that mean about the underlying Cauchy problem? This is why I started with the original ODE plus IA over here. Because if we push it to the other side, I get minus IA. Remember the first main theorem on semigroups. U prime is equal to the operator acting on the other guy. The operator is minus IA. Push it back over here. You get u prime of t plus I a u of t is equal to 0. U of 0 equals u0 if, so here's the main caveat. Everywhere I needed that x belongs to the domain of the underlying operator, not the entire space. So this evolution equation is well posed, provided the initial data is belonging to the smaller space, the domain of the underlying operator. So Stone implies if you can show that A is self-adjoint, then this guy well posed. So let me end by saying who cares? And it's not just me who cares. So equations of this form in a Banach space have been studied actually quite a bit. Again, first by Stone, and then Neumann, and then in the 50s and 60s came along Jacques-Louis Lyon, Yoshida, Toshio Kato, Nierenberg. So lots of analysts have papers on equations of this form in a Banach space, where they study, for example, the spectral properties of the underlying operator A. For example, in the first, remember the estimate I gave you in the first part of the theorem, which says that the operator norm is controlled by this guy, m e to the omega t, omega positive. So if this is going to be the solution of some evolution equation, you want to see when it decays in time, you want to find an optimal bound for this, which is going to be related to the spectrum of the underlying operator A, so you have to study the spectral properties of this guy. And this has been done a lot by these guys. And so the last thing I'll say is what equations can we make look like this? Well, the first one I talked about today was in quantum mechanics. You had the Schrodinger equation. So A is going to be your Hamiltonian. So show your Hamiltonian is self-adjoint. Boom. Okay, for the physicist, every Hamiltonian is always self-adjoint. But if you're a mathematician, you actually want to show that it's self-adjoint. So quantum mechanics analog, the one that I study is the electromagnetic analog. It's not the wave equation. I can study full Maxwell equations in this form. So you have Schrodinger, you have Maxwell, you have a linearized Navier-Stokes / acoustic equations. So there are many different equations you can put in this form. And using the resulting, as long as you can show that the underlying operator is self-adjoint, you have this whole semigroup theory and Stone's theorem that gives you well-posedness of the Cauchy problem. All right, so I think that's a good place to stop. Thanks for listening.